Welcome. In this video, I'm going to go over how to compute the volume of some more irregular shapes, like say this one below. And from the guided lecture, you should have looked at what the volumes, say, of a rectangular prism and a cylinder have in common. And what they have in common is that their volume is equal to the area of the base. In the case, it's the length times the width. In this case, it's the area of this circle, which is pi r squared, times the height of the three-dimensional shape. We can apply that to an irregular shape like this. So the first thing we need to do is let's mark our axes. Okay, so as you can see here, what we're used to looking at is this two-dimensional plane. That's the x-axis and the y-axis here in green. But what we have now is we have this other part, the z-axis. And so now we're going to sketch another plane, and I'm going to sketch this plane so it is here and it is perpendicular, so it intersects the x-axis at a right angle. Okay, so there is my plane, and I'm going to label it P sub x because this plane, as you can see here, is perpendicular to the x-axis. And this plane intersects this solid here. So this plane is intersecting this solid. Well, when it intersects it, what kind of slice do we end up with? Let's sketch that. So we end up with a slice that looks kind of like this. And this is a single slice taken by intersecting this plane, which is perpendicular to the x-axis. So what we call this slice is a cross section. Let's go ahead and sketch out that slice as it looks on this plane here. So we're just going to sketch this two-dimensional image. So this cross section is what a single slice looks like. So when a plane is intersected with this figure. Okay, now that we have this slice, what is the area of this slice? Well, we can denote the area of this slice as AX, A of X. Now that we have the area of this slice, we can begin to discuss the volume of this slice with some thickness. So say I made the slice thick, that is, say I cut a wedge out like this. What is this distance here? If you notice this distance, you start at some x value and then you go to another x value. So it's the distance between two x values. So this is the change in x. So the thickness of that slice is the change in x. So let's go ahead and sketch the three-dimensional slice now. And let's do that over here. Okay, so there is that thicker slice, that three-dimensional slice. And if you recall, this distance here is delta x. And then the area, so let me shade this front part in. The area of this slice is A sub x. Now, how can we use the concept we learned before to compute the volume of this thicker wedge slice here? If you said we multiply these, you're correct. We want to take the area here and multiply it by this thickness. That's equivalent to what we did before, which is where we got the area of the base and we multiplied it by our height. So now we're taking the area of this two-dimensional portion and multiplying it by this thickness. So the volume of this thicker slice is A of x times delta x. So that is, this is the area of this cross section of this shape with this plane. And this is the thickness here of our thick slice. Okay, so this is helpful, but what I really want to do is find the volume of this entire shape. And so far, I only have the volume of this wedge in the middle here. So what can I do? All right, so what do I have here? As you can see, I went ahead and sliced this region into 9 slices, and the height across the board is uniform for these. And the thickness of each of these slices is uniform. And I went ahead and left one shaded in red just to make it clear that this is kind of our original representative slice. And now, in order to find the volume of this entire shape, I could find the area of the front of each slice, and I'm going to highlight 3 of them, and multiply that area of the front of each slice by delta x, since all of these distances, that is, all of these thicknesses are the same and they are all delta x. So this is delta x, this is delta x, this one, and so on. They are all equal to delta x. Now this is just an estimate, of course. It's kind of like when we first learned integration, when we learned Riemann sums, and you wanted to find the area under a curve. We started with these rectangles, and they weren't very accurate. We had to get more and more and more rectangles. So in the same way, we need more and more slices. As you can see here, I went ahead and copied this figure 3 different times, each with a different amount of slices with some thickness here. I have 10 slices here, so I'm calling this first one S1. This second one would be S2, and so on. This is S9, and this last slice is S10. And then on this second one, it's about 20. So I have S1 here and S20. And on this last one, I have 1 through 30 slices. And as you can see here, our thickness, our delta x is larger here. And delta x here is smaller. That is, these slices have more thickness than these ones. This means we have less slices. And here we have more slices. Now let's use these slices and delta x to estimate the volume of this larger shape. As you can see in the above sketches, the volume of each slice, Si, so this would be S1 or S2 or maybe all the way up to S30. So the volume of each individual slice is the area of the base multiplied by its thickness. And the thickness is delta x. So that is the volume of our solid can be seen as A, the area of the front of a particular slice times the thickness of that slice. Now, of course, this volume formula here is only useful if we have a finite number of slices, 10, 20, 30, but that's not really going to help us get an exact value of the area. All of these will be estimates. So what we really want, we want to add up an infinite number of slices, and for that we need a limit. We need the limit as n approaches infinity of the sum running from 1 to n of the area of an infinite number of slices times the thickness of each slice, delta x. Now before I continue, let's label our x-axis a little better. Let this point be A here and this point be B. This means that this shape along the x-axis runs all the way from x equals A to x equals B. Now what this summation here below tells us is that we can actually use an integral of the area of a representative slice, so of a representative cross-section here, from A to B to compute the exact volume of this shape. I hope this video was helpful.